Yeah, I think we should be all right. Hopefully, folks can hear me all right in the back. Okay. No, I think we're fine. So first of all, thank you for having me. I appreciate the invitation, Sam. Just a little bit of background for myself. I was actually trained as an economist, so please don't hold that against me. Actually started my career of all things in trade economics, focused quite a bit on intermodal shipping. You'll probably see a little bit of that in my presentation. But I spent the vast majority of my time, thank you very much. Spent the vast majority of my time actually in the intelligence community, a little over 15 years, both at the National Security Agency as well as CIA, focused quite heavily on cyber operations. So I come at the problem of smart cities more from some of the security concerns. And so what I wanted to talk to you about today was some of the complexities when thinking about security of smart cities. So let's see if I can work this appropriately. There we are. So the first thing that we really need to think about is this notion of strategic risk. So after I left the intelligence community, I moved to first the private sector, did quite a bit of work for the Fortune 500 and other government agencies, both here in the United States as well as around the world. And it was apparent to me, just having a broad set of discussions with policymakers, that the notion of strategic risk, while extremely important to folks, wasn't well defined, wasn't well quantified. And this became a real issue when it really boiled down to what types of cyber attacks we should actually respond to as a national government. And the example that I always like to give my students is, if there's an attack on Joe's Crab Shack, does that constitute a national emergency and therefore we need to respond? Or is that something that's really more of a private concern? And so the difficulty in this is obviously, that's a pretty straightforward example. But when you start talking about attacks on critical infrastructure, specifically organizations involved in those sectors like BG&E, well, it kind of depends. Because there are some types of attacks, like a website defacement, that you may not really care that much about. There are other types of attacks against industrial control systems that you might actually care quite deeply about. And so the ability to quantify the expected consequences of attacks is really all about understanding complex integrated systems. And I've heard some of the other speakers talk about that, and that's exactly the way that we think about it at the University of Maryland. And this is not a revolutionary concept, right? In fact, we see it in our policy documents. The recently released National Cybersecurity Strategy specifically talks about a comprehensive understanding of national level risk. And they're specifically talking about it in terms of critical infrastructure. How do we actually understand it? How do we quantify it? How do we actually put it all together? And this is actually a really, really difficult problem. And so the first thing that I wanted to do today is I wanted to kind of give you an illustration of what do we actually mean by complexity, right? And so again, I told you that I was a, let's see if this works here. I told you that I started off my career in economics, specifically trade economics. So I like to use examples in intermodal transit because I think it helps identify the complexity and the significance of the cybersecurity threat that we potentially face. And then I'm going to apply that to a smart city initiative here locally in Washington, D.C. So let's assume I have a 4-year-old daughter and she loves stuffed animals, but let's say that we are talking about the shipping of Beanie Babies from one point of the earth to the next. How is that actually done, right? And most of us, we never think about these things unless you've actually worked in trade and transportation. But it actually starts off with a particular shipper. And that shipper then has their own IT networks, their own software applications it leverages. And then it makes a call to, let's say, a trucking company. That trucking company then disperses trucks, uses its own fleet management software, its own internal IT networks. They bring it to a rail ramp, right, where it's loaded onto a train. That train has its own SCADA systems, has its own management distribution systems, its own communication systems, all supported by its own IT infrastructure. The container gets moved cross country, gets dropped off at another rail ramp, it gets picked up maybe by another trucker, again, using its own systems. And that container then gets brought over to, let's say, a marine terminal. That marine terminal, it's picked up off the truck and it's put on the ship. That ship has its own propulsion systems, has its navigation systems, all supported by IT infrastructure, all with its own vulnerabilities, all with different access vectors. And so as you play this out, and as that container moves from point A to point B, there might be as many as 40, 50, 60 different IT systems it comes in contact with. So I, as an attacker, have a very, very large attack surface that I can go after. So the concern then is, how do you actually start managing those shipping networks? How do you manage the risk to all of it? Whether you're talking about trail or trucks, rail, port systems, you have to have a deep understanding of it. And as a policymaker, or even as just an organizational leader like the head of Marisline, how do you manage that complexity? And that's really, really difficult. Okay. So what does smart city complexity then look like? So I took, and I know it's a little hard to read, but this was an announcement last month that talked about Mayor Bowser basically talking about partnering and to actually bring in smart traffic light systems into the district. And so, obviously very, very excited about this new data sharing program. And they talk a lot about connecting with Audi and some of their new systems. Okay, so what would that actually look like? And we've referenced, through the course of the day, some of the technologies. And so let's, use my little simple cartoon here. Just one really simple intersection. What would that potentially look like in terms at a very high level? What kind of systems have to work together in order to make that happen? Okay, so this is a very, very simple node edge map, and it's a little hard to see that there are actually links here. But let's assume, we've got just a handful of cars, and cars themselves are also quite complicated. They have their own networks, they have their own systems, their own software, their own vulnerabilities, right? But they connect actually to sensors, right? These street sensors here. So they connect to that. There's just a handful. But then those sensors may have connections to PLC controllers, right? Those are going to be connected at some point to the wireless infrastructure. Okay? This is just a handful of, cell phone towers right here, right? Remember, this is just one intersection. Just one intersection. Okay? Well, now you got to worry about the IT infrastructure for the cellular provider. Let's say it's T-Mobile. There's a whole other network that you got to worry about. So it's just kind of a representative network diagram. There are all a bunch of different ways that I could potentially get into that network, right? That T-Mobile actually interacts with internet service providers, the whole AS structure of the internet. That's how packets move, from one point of the earth to the next. So T-Mobile may be interacting with, AT&T. AT&T might be working with Sprint. Sprite too, I guess. At the end of the day, it's eventually going to make its way, maybe some of those packets are going to make its way back to, let's say, some office building in DC that has this management system, or a portion of it, right? And so that particular system might have its own set of networks, all with its own vulnerabilities and access vectors. I, as an attacker, could go after their supply chain. I can go after the human dimension, so I can try to spearfish folks. I could look for remote vulnerabilities. All these different ways I could potentially get in, right? So I've just highlighted, just from that, well, that's pretty, that's a pretty big attack surface. But guess what? These systems, and I forget which speaker talked about it earlier, also use a lot of machine learning or AI systems And those systems are deployed, guess where? In the cloud. That cloud data center is not in that municipal building. It's in a different part of the internet, right? And guess what? These cloud systems, the way that they're designed is that you're looking for scalability. You're looking for the ability to be agile. So you're going to, let's say, have some failover and some redundancy where it allows those, let's say, systems to, fail over from one data center to the other. Well, guess what? They are all interconnected through the internet, through those various AS structures, right? So I, as an attacker, can go after lots of different things. We oftentimes, when we talk about this technology, we tend to talk about vulnerabilities in sensors. But I'm here to tell you that why would I do that? That's a lot of work to go after one sensor. Why don't I just go over here? Or why don't I just take out this or this? Or maybe if I'm interested in collecting data, I can do something like a BGP hijack. So I, as an attacker, have lots of different ways I can come at you. So again, this is all for just one intersection. So imagine that this is replicated 10,000 times. That's a really, really big attack surface. Lots of engineers who have access, right? I'm going to do my research. I'm going to do my reconnaissance. I'm going to find out who those people are. We did a project in Tokyo ahead of the 2020 Olympics. The Japanese government brought us over there to conduct a workshop to talk about complexity, talk about the attack surface. And one of the things that they were deeply concerned about was the electrical grid. Of course, makes perfect sense. They had one view of cybersecurity for the electrical grid. Make sure that they lock down those industrial control systems. It's a good place to start. I would absolutely, totally agree with that. But they didn't think about the smart meter network. I can do a lot with smart meters, an awful lot with smart meters. So again, that growing attack surface is really, really important. So part of the problem here is understanding the motives and the actors that you're trying to go against. But if you understand their motives, then it gives you at least a good idea of where they would go after, right? So some, as we know, some threat actors, are pure hobbyists. They're just interested in how the technology works. They're going to play around. But they tend to be lower skilled, and they tend to have fewer resources. They might be hacktivists, they may have a political agenda, so they're engaged in things like website defacements, maybe some denial of service type activity, certainly criminal networks and nation-state capabilities, but they have a variety of different motives, and understanding those motives gives you an advantage as a defender. Because you know your network and you know what services are provided, and if you understand the motives, then you can understand what you probably need to protect. So if one example of, let's say, a particular type of attack is that, maybe I'm an advanced persistent threat actor, I'm a nation state, and I'm seeking to engineer some sort of disruption against your signaling network. And so one thing I might do is find my way into that, let's say, that local network in the DC, one of the DC offices, and I'm going to throw ransomware on a particular device after I've manipulated the control systems. And I can do that if I have, let's say, administrative privilege. And then I'm going to brick it, and then you're not going to be able to do anything for it, with it for maybe 6 hours a day, 2 days, 3 days. It depends. Depends on what are the procedures that you've been able to push through in your organization. So that becomes a real problem. We've actually seen examples of something like this, the Ukraine power event, where roughly 100,000 homes were left without electricity in Ukraine. It was actually 5 different effects that were engineered. Most people only talk about the loss of power, but there were actually several. But one of the methods that they used was they actually got access to the human-machine interface, and they used basically just administrative credentials, and they used the software as it was designed to take the breakers, or to flip the breakers. But right after that, they dropped what's called a wiper, and they completely obliterated the operating system that was running on that device. And it took a little while for people to reconstitute. They also did some really interesting things too, like they had access to the PLC controllers, and they put a little piece of software on there that anytime that remote system tried to access the breakers, it would just drop the packets, which made it a lot harder. So they actually had to send people out in the field to actually do it manually. And they also did something really clever too. They manipulated the uninterrupted power source, the UPS system, so that they were basically in the dark. So they actually, they were using their cell phones initially until they could get power on. So there's lots of clever things that we can do to make life miserable for you. So by hitting, let's say, or deploying that ransomware, I can be successful and create serious problems. It's interesting. There was a paper recently put out at Georgia Tech by a couple of researchers last month, where they looked at New York City, and they were able to identify that if only 10% of cars were, in this case, they were looking at autonomous vehicles, but were able to engineer some accidents with just 10% of the cars in Manhattan, they can completely shut down the city, right? So you see this emergent effect occur where you go from the primary effect on the network to this emergent phenomenon in the city, right? So, but there are other tactics I can use. Ransomware is just one of several things I can do, right? So another example might be, well, maybe I leverage the inherent vulnerabilities in IoT devices and assemble a very large botnet like Mirai. And I use that botnet army to do things like, I don't know, oops, see if I can go back. Let's see, how do I go backwards on this? Well, I'm sorry? Oh, I am back, okay. So I can actually go, I can use that IoT botnet to potentially hit the load balancer or the DNS infrastructure ahead of that data center. And in fact, we saw that exact scenario play out with the Mirai botnet. They went after a company by the name of DIN, which provided DNS services for that data center. They didn't do anything to the virtual machines running in the data center. They hit the architecture. And when they did that, they took a lot of companies offline for a period of time. Companies you probably have heard of, like Netflix, right? Or Etsy, right? So maybe you don't care about Netflix. Maybe, it's like you can watch your Netflix shows, later on. But increasingly, we're starting to see cloud and data center services being leveraged for critical infrastructure. For these types of management systems that you guys are talking about, machine learning, AI, all this stuff is going to be run in this kind of distributed environment. So you have to understand this broad attack surface and the tactics that are used to potentially disrupt. Okay? So that becomes a real problem. But the problem is that this is not just about a single service. This is not just about traffic signaling, right? And so, what you have to be worried about are all these different services: water, smart grid technology, signaling, right? And each one of these have different sets of networks, graph structures. So we think at the University of Maryland, this is actually how we approach this problem, is you've got to start thinking about how these things are interconnected. Because oftentimes in the risk management field, what we tend to look at are basically just a list of devices that we think are important. Like this one application server is running my signaling technology, so I got to make sure I protect that. Well, that's great. I agree. That's one thing you have to protect. But you might also have to protect the routers in between. You might also have to protect the end users that are there because they work together as a system. And if you've protected one element of that, that's great. But if I hit you somewhere else, I can probably achieve the same effect. And that's exactly the way that, those of us on offense, that's how we think. So if we're going to be on defense, we got to do the same thing, right? So the problem then for policymakers is that you've got multiple organizations that are involved here, right? You got the municipalities, right? You've got the internet providers, you got device manufacturers, you have data center operators. They don't all report to the same boss, right? this multi-stakeholder governance problem that we've got to deal with. And that is part of the problem. So when we talk about governance structures, like, we have to start asking questions, if we're a policymaker, about, what are the what are the most significant types of attacks we're most concerned about, right? That's got to be number one. How do we just categorize them? How do we just talk about them? How do you measure that risk to the network, to the organization, to society? How do you quantify it, right? So, and these things are interlinked. We argue that for any given particular cyber attack, that there's going to be multiple effects. There's the direct effect on the network, but then there's kind of this effect to the organization, could, in terms of, brand impacts or financial loss. And then, of course, there could be second order effects, to broader society. And attacks, the way they play out, you've got to be able to quantify that. I'll give you two examples. So there was a ransomware variant called NotPetya. Some of you may have heard about it. And it was actually engaged as part of a broader conflict between Russia and Ukraine. Russians will never admit it, but that's no doubt what was going on. And the Russians did something very interesting, or ostensibly the Russians did something interesting. And they got access to a particular organization. It's kind of like the TurboTax of Ukraine. And they got access to what are called update servers. And oftentimes, your software needs to be patched for vulnerabilities, right? And it pushed out the ransomware instead of a legitimate patch. So thousands of devices and networks in the Ukraine ended up getting bricked. One of those organizations was Marisline. It's the world's largest container ship company, and they actually had a satellite office in the Ukraine. Now, this particular ransomware variant also had a way of propagating. So it moved through the network and eventually got access to 6 very specific application servers in Marisline's network. And they engineered a worldwide shutdown of all marine terminal activity in Maris for 3 days, and 7 of their largest terminals for 2 weeks, including Rotterdam, which is Europe's largest container port, Port Elizabeth in New Jersey, Los Angeles. It cost Marisline $300 million. $300 million in lost revenue. It was huge. The societal impacts, especially in Central Europe, were a massive logistics bottleneck, right? So that's one example. And that's a pretty bad example. Another example is a simple website defacement. Who cares about website defacement? You change it back in 5 minutes, no big deal. Well, in this particular case, this website defacement occurred in the country of Qatar. So, Qatar's in an interesting region, and they have, their view of regional politics. And some actors, ostensibly from the United Arab Emirates, had gotten access to the state media company's website and had basically subtly put in some articles that were manufactured about how the Emir of Qatar was actually more pro-Iran than they actually were, and was really trying to stoke up some resentment against the Qatari government, led to protests in the streets, and eventually actually helped engineer a large-scale blockade with the participation of the Saudis and the Emiratis, all from a website defacement, right? So very minimal primary effect, very minimal secondary effect. Second order effect is massive. So you've got to think of these types of effects in, with a little bit more complexity. Okay, so how do we actually do it? We got to be able to categorize it. We got to be able to measure it. We've got to be able to tie it all together, and then really talk about how those effects on a single organization affect the larger system. So at a very, very high level, we think of how to categorize effects either as disruptive or exploitive. We have a taxonomy of effect. I won't bore you with it, but we actually break it down at a very, very high level between those two types of events. Disruptive events being, impacts on your ability to execute your mission, and exploitive effects being basically the removal of data from your network. But again, it's regardless of the tactics that are used, what I'm interested in is the effect that is engineered. We have a couple of ways of measuring effect. We've developed a couple of graph-based indices. One is what we call the CDI, or the Cyber Disruption Index. The other is the Cyber Exploitation Index. And so we have a repeatable way, based on the tactics that are used and the end effect that's achieved, a way to quantify severity against the network itself. This is the first step in trying to get a better handle on complexity. Okay? We try to put it together, and what this diagram basically represents is surface map. So if there's a network topology under shipping and payroll and customer service, we run it against a variety of different end effects, and we generate scenarios. And from that, we have a much more detailed understanding of risk against the network. Because again, oftentimes when we look at these things, we tend to pick one attack method. People will say, well, what's the effect of a cyber attack? And in our head, we think, oh, well, I'll just assume it's a denial of service attack. Well, guess what? That's just one type of effect that can be engineered. You've got to be much more nuanced. And so we expand that out. And what that allows us to do is have a much better sense of what the end effect might be. Okay? And then finally, any one of those organizations are probably operating in a larger system up outside of that organization. This is just a very, very simple representation of the Mid-Atlantic Intermodal Transit Network, right? So it includes rail ramps, it includes, port terminals, and the size of the nodes here represent that kind of organizational risk that we computed in the step before. I'm going a million miles an hour, and it's a lot more detailed than that, but this gives you a high-level sense of how to start working through, an attack on a specific entity and how that bubbles up into this kind of systemic risk in the system. And I would argue that if we don't do this, and as we deploy this technology, we are opening ourselves up to some very, very significant strategic effects. And I'm deeply concerned about this as a security researcher, because when I think about how we might respond as a government to these types of attacks, it becomes really quite concerning. The most recent nuclear posture review that came out from the current administration talks about the potential use of nuclear weapons in the cases of strategic cyber attack. But it's not defined anywhere. When you look at PPD 41, which is the policy document that actually talks about national response and actually uses for the first time the term strategic attack, makes a differentiation. They say, well, hey, we're going to make a difference between the attack on Joe's Crab Shack versus BG&E, but there is no method for them to define that red line. So if it's that ambiguous, how do adversaries in the space understand what is crossing a threshold? We need to get better at that. We need to articulate it. We need to be able to categorize and quantify. So that's really kind of the area of focus that we have over at the university. So I think that, so the challenge here, just to wrap up, we need to be able to better understand and map smart city infrastructure, right? We need to be able to model threat actor scenarios. We need to be able to estimate local effects. And we need to understand how that works in kind of an integrated system and figure out means of proper governance. How do we balance the benefits of the technology with security considerations? So hopefully I didn't bore you, but I'll leave it there. And I'm not sure if we have any more time for questions, but
we have a panel.
That's right.
In plenary.
Okay, great. Thank you very much.